last lecture we have constructed a Lagrangian density for the Dirac spinner, and the Lagrangian density is given by psi bar I gamma mu del mu minus m psi, from which we can derive the equation of motion, and the equation of motion for psi is given by I gamma mu del mu minus m psi equal to 0. This admitted both positive frequency as well as negative frequency modes. They are given by psi equal to u of p e to the power minus I p dot x. So, if we try to look for a solution of this kind, then we see that there are two linearly independent solutions. So, there are two linearly independent 4 component spinners, which I call as USP, and if I look for a solution which is of the kind psi going to V of p e to the power I p dot x, then again there are two linearly independent 4 component spinners, which I will denote as Vs of p. These where S runs from 1 to 2. So, these spinners USP and VSP, they satisfy a number of identities which we have derived in the last lecture, which I will summarize here. U bar R P US P equal to delta R S, then V bar R P V S P equal to minus delta R S, and then sum over S U S P U bar S P equal to P slash plus M over 2M. Then an analogous statement for V, which is sum over S Vs of P Vs bar of P equal to P slash minus M over 2M, and a number of identities in addition to all these things. What we will do is that we will use these solutions these linearly independent solutions to construct the most general solution, and then we will see what happens when we quantize the Dirac field. Okay. So, the most general solution will of course be a linear superposition of solutions of these kinds. Therefore, psi of x can be written as sum over S integration dq p over 2 pi cube, and we will use a slightly different normalization m over omega p. You can see that this is again Lorentz invariant, because m is the rest mass of the particle, which is a Lorentz invariant quantity, and this integration measure we have already seen is Lorentz invariant. Then the coefficients, I will call them Cs of p US p e to the power minus I p dot x, and then ds dagger of p Vs e to the power plus I p dot x. This is for psi. Now, let us try to look at what is the conjugate momentum to the field psi. Okay. This is given by pi psi. If I call to be the momentum conjugate to psi, then this is del L over del 0 psi, and from the expression for the Dirac Lagrangian you can see that this quantity is given by psi bar times I gamma 0, okay, which is equal to I times psi dagger of x. So, you might think that the equal time commutation relations again will be something of this kind. Psi of t x pi psi of t x prime equal to I delta x minus x prime. However, we have already seen if we have commutation relations of these kinds, then we get some commutation relations for these operators Cs and Ds daggers, and then this gives us a spectrum for particles which obey Bose-Einstein statistics. Okay. We do not want particles of spin half integer to obey Bose-Einstein statistics, we want them to obey the Fermi-Dirac statistics, and that cannot be achieved by considering a commutation relation between the field and the conjugate momentum. What we will do is, we will, instead of commutation relation, we will have anti-commutation relation instead, and then we will see what happens when we consider the anti-commutation relation. Anti-commutator of the field and the corresponding conjugate momentum is I times delta x minus x prime. This is what we will assume, and then we will correspondingly get some anti-commutation relations between these operators CSP and DS dagger P. We will see that these anti-commutation relations give a spectrum of particles which obey the Fermi-Dirac statistics. So, this amounts to saying that psi of x t psi dagger of x prime t, the equal time anti-commutation relations is given by delta x minus x prime. We can use this anti-commutation relation and derive the corresponding anti-commutation relations for CS P and DSP. Instead, what I will do is, I will give the anti-commutation relations for CS and DS, and then we will check that this anti-commutation relation is satisfied provided these operators CS and DS dagger satisfy the following anti-commutation relations. So, the anti-commutation relation satisfied by the CS and DS is given by CRP CS dagger of P prime, anti-commutator is given by 2 pi cube omega of P divided by m delta P minus P prime delta Rs. And similar relation for the D's, dr of P ds dagger of P prime is equal to 2 pi cube omega of p divided by m delta p minus p prime delta res, whereas the anti-commutation relation between C r of p, C s of p equal to 0, C r of p ds of p prime equal to 0, and C r of p ds dagger of p prime equal to 0, and then the conjugate of these two equations, the Hermitian conjugate of these two equations. So, these are all the anti-commutation relations satisfied by these operators C's and D's. What we will do in the following is, we will assume these anti-commutation relations, and then from there we will derive the anti-commutation relation for psi and psi dagger. Okay. So, let us do that.
What will happen if we impose the commutation relation on this pi side?
Then you will get here, you can, I mean, just like the case of a complex scalar field, you will have commutation relations here instead of anti-commutation relations. Then you try to construct multi-particle states from the vacuum. So, how the multi-particle states are constructed? A dagger of K1, a dagger of K2. Let us consider a 2-particle state, okay, constructed out of vacuum. Because a dagger and a commute, therefore, this K1, K2 is same as K2, K1. The state does not change under the exchange of the quantum numbers here. So, that is why these particle like states actually obey the Bose-Einstein statistics. What we would like to have is, we would like to have these particle like states obeying Fermi-Dirac statistics, and hence you would think that these operators should actually obey some anti-commutation relations. That is the reason we start with an anti-commutation relation for the field and the corresponding conjugate momentum. Okay, so let us derive this equation from these relations. I will consider the components of these spinors here. It will be easy for us to do the computation in terms of the components. So, the components here, both psi and psi dagger are 4 component spinors, and what I would like to consider is psi alpha of x t anti-commutating with psi dagger beta of x prime t, the equal time anti-commutation relations. I already know what is the expression for psi, okay. This trivially tells me what is the expression for psi dagger. What is psi dagger? It is sum over s integration dqp prime I will use for the integration variable, and for this one I will use r 2 pi cube m over omega of p prime Cr dagger of p prime u s dagger of p prime u r dagger of p prime e to the power minus I plus I p prime dot x prime. Here I am considering x prime, and this one plus dr dagger of p prime, dr of p prime, vr dagger of p prime e to the power minus I p prime dot x prime. Okay. So when I take the anti-commutation of this with this, I will consider psi alpha of x. So there will be a us alpha here, there will be a vs alpha here, and similarly I will consider psi dagger beta. So there will be a betath component of ur p prime and betath component of v dagger r of p prime. Now what will I get for this anti-commutator here? It will, so the first term and this, it will give some anti-commutator here which is non-zero. Then anti-commutator of this term with this term trivially vanishes because of this relation here. Similarly, anti-commutator of this with this will vanish because of the conjugate of this equation, Hermitian conjugate of this equation, and then the anti-commutator of this with this which is not going to vanish. So these are the terms which are going to survive, the anti-commutator of this with this and the anti-commutator of this with this term. So let us look at these two terms. In fact, I can call this to be psi plus and this to be psi minus, then psi plus psi dagger minus and psi. So these are the commutation relations which are non-vanishing. These are the anti-commutation relations which are not vanishing. So this is sum over r, sum over s, and then you have integration dqp divided by 2 pi cube m over omega p, and again you will have integration over p prime which is dqp prime over 2 pi cube m over omega p prime, and then there will be two terms. I will erase this and so this times the anti-commutator of Cs of p, C r dagger of p prime and then us alpha of p, ur dagger beta of p prime, and then e to the power minus I p dot x minus p prime dot x prime. This is the first term, and similarly I will have one more term which is given by ds dagger of p dr of p prime vs alpha of p vr dagger beta of p prime, and then e to the power plus I p dot x minus p prime dot x prime. So This is what we will get. These are the two non-vanishing terms. Now, let us simplify this. We know what is the anti-commutation relation here. It is just up to some normalization, it is delta R s times delta p minus p prime. So, let us substitute that. We will substitute that and then we will carry out the p prime integration. Okay. So, if you substitute that, because of the Kronecker delta R s, the sum over R we can just carry out and then it will be a sum over u s alpha p u s beta dagger p prime, but there is a Kronecker, there is a Dirac delta of p minus p prime, which will make both this p and p prime equal if you carry out the p prime integration. Now, look at this term here. This term is e to the power I, the e to the power minus I, p dot x is omega t minus this 3 vector product p dot x, and then here p prime dot x prime is minus omega prime of omega of p prime is what this 0th component of p prime dot 0th component of x prime is t, because we are considering equal time anti-commutation relations. So, omega prime of p t and then plus p prime dot x prime, this 3 vector product. So, because the whole thing is multiplied by delta Dirac delta of p minus p prime, therefore, I can substitute here instead of in the place of p prime I can just write p, then the t dependence will cancel from here and here. So, what you have is e to the power plus I p dot x minus x prime. That is what you are going to get here when you carry out the p prime integration. Here instead, when you carry out the p prime integration, because of the opposite sign here, what you will get here is everything will be the same except that you will get e to the power minus I p dot x minus x prime, right. This is what we are going to get. So, let's carry out the computation. So, this sum over R will go away because of the Kronecker delta. So, you will have only sum over S and then integration of dqp over 2 pi q m over omega of p. This m over omega p prime will cancel here this normalization omega over m, okay, and this 2 pi q again will cancel this 2 pi q, and I am carrying out this dq p prime integration. So, the Dirac delta will go away. Finally, what we will be left with is u s alpha of p u s beta dagger of p again because of the integration over p prime, and then e to the power I p dot x minus x prime, whereas in the second term I will have a plus v s alpha of p v s dagger beta of p e to the power minus I p dot x minus x prime. This is what we will get when we substitute for the anti-commutation relations for CS and DS and so on. Now you look at the sign here, here it comes with a plus sign, but here it comes with a minus sign. If I want to take this as a common factor, what I can do is, in the second term for example, I can change this integration variable p to minus p, and when I do that, here I will have a plus sign, but in the arguments will of Vs will change the sign, right? Yes or no? Okay, so let's do that. So therefore, what I will have here is Vs of minus p and Vs dagger beta of minus p, and here I will have a plus. Now we can just take this out. So sum over S dq p over 2 pi q m over omega p, and then e to the power I p dot x minus x prime, and then us alpha of p, us beta dagger of p prime, p again, plus Vs alpha of minus p, Vs dagger beta of minus p. So it almost looks like we are having a Dirac delta function here, but it's not yet, because of this term in the inside the square bracket. What is this quantity here? When you carry out the sum over S, what do you get? Okay, so in the beginning of this lecture, I have written down some of the identities that we have proved in the last lecture. One of them is, if you carry out the sum over S, us p us bar of p, right, then this quantity is p slash plus m over 2m. Here instead you have us dagger. So if you want to get an expression for us dagger, you get some, you just multiply gamma 0 from the right. So this is simply us p, us dagger of p is 1 over 2m p slash plus m gamma 0. Similarly, sum over S, Vs of p, Vs dagger of p is 1 over 2m p slash minus m, right, gamma 0. What we want instead is Vs of minus p, Vs dagger of minus p. So the second line implies sum over S, Vs minus p, Vs dagger of minus p is equal to 1 over 2m, p slash is gamma 0, sorry, p 0 gamma 0 minus pi gamma I, because of the minus here. So you cannot simply have a minus sign here, because this 0th component does not change the sign, okay, and minus m whole thing multiplied by gamma 0. Whereas this one here you can see is given by 1 over 2m p0 gamma 0 plus pi gamma I plus m whole thing multiplied by gamma 0 from the right. So, if you add this term with this term, then what you get is the last two terms cancel each other and the first term adds. So, you have sum over S u s of p u s dagger of p plus v s of minus p v s dagger of minus p is given by 1 over m p0 and there is this gamma 0 square which is identity. So, it is just simply given by p0 is nothing but omega of p divided by m, alright. If you want to put the alpha, beta, etc., then this is just delta alpha beta. So, us alpha, us dagger beta and vs alpha minus p, vs dagger beta of minus p is simply given by this times delta alpha beta. So, there will be a delta alpha beta here. So, what we have seen here is after doing all this calculation, this thing here inside the square bracket is nothing but omega over m delta alpha beta. So, let us substitute that here. Sum over S is gone. So, dq p over 2 pi cube m over omega and then e to the power I p dot x minus x prime and the whole thing is given by omega over m delta alpha beta. So, m over omega cancels omega over m and hence I can carry out the integration over p when I do that what we get is psi alpha of x t, the equal time anti-commutation relations, psi beta dagger of x prime t is nothing but delta of x minus x prime delta alpha beta. So, in order to have the 4 component spinner, the Dirac spinner and its conjugate momentum to obey the equal time anti-commutation relation, what we saw is that we need the coefficients C s of p, C r dagger of p prime to obey some equation like 2 pi cube and omega over m delta of p minus p prime delta r s and so on. So, now as you may have expected already that the CS act like annihilation operators, whereas the CR daggers act like creation operators. Again we will have a vacuum, we define 0 to be the vacuum state which is annihilated by CR P for all P and for R equal to 1 and 2, and also it is annihilated by ds of P equal to 0 for all P and for R and S to be 1 and 2. Then the multi-particle states are constructed by Cs dagger of P acting on the vacuum and so on. dr dagger of P prime acting on vacuum and then a bunch of C's and D's acting on this vacuum. So, this way you can construct the entire Hilbert space, and then you can see that because of anti-commutation relation like this, these particle states actually obey the Fermi-Dirac statistics instead of the Bose-Einstein statistics. You can construct the energy momentum operators and the charge and so on, because the Dirac Lagrangian, as we have seen, has a U1 invariance, it has a global U1 invariance. So, there will be a conserved charge. You can construct the charge operator, you can see that if these are, I mean the charge for these particles are actually opposite to the charge of these particles of the second kind. Okay. So, if we identify this with the positively charged particles, then these will be the negatively charged particle or vice versa. So, for example, if these are the electron states, these states represent the electron, then these states will represent the positrons. Some of the important things that you must note is the following. For example, when you consider the normal ordering, okay. In the case of bosonic fields, we were saying that if we have a bunch of operators and then we just consider the normal ordering of these operators, then what we have is this: A of k, a dagger of k prime, A of k3, A of k4, a dagger of k6, something like this. Then what do you have? What do you get? You just, for bosonic fields, this is just given by a dagger of k prime, a dagger of k6, and then a of k, a of k3, a of k4, right? This is all you have. Now, in the case of fermionic operators, you have to be a little bit careful about moving this to the left. If it crosses one of these operators, then it changes a sign. So an identical, a similar relation for the fermionic operator will have this. C, I am suppressing the spin indices, C of k, C dagger of k prime, C of k3, C of k4, C dagger of k6. Let us say you have normal ordering of these operators, then you see here this operator will have to come once, therefore, it will change the sign. This is just normal order product of minus C dagger of k prime, C of k, and then C of k3, C of k4, C dagger of k6. But again, this, if you want to bring it to the extreme left inside the normal order product, it will change the sign 3 times. So, this is minus 1 to the power 4 and this is Cs dagger, C dagger of K6. So, this is simply minus 1 to the power 4 C dagger K prime C dagger of K6 C of K C of K3 C of K4 without any normal ordering. If there was one more operator here, then for the bosonic fields it would not make any change, but for the fermionic field it will gain a minus sign. So, you have to keep track of these minus signs also. If these operators, if you cross this operator once, then it will have a minus sign. So, that you need to be careful about when you do the normal ordering. You go and work out the expression for the energy momentum tensor. What I claim is the total energy momentum has the expression which is given by d cube k over 2 pi cube m over k 0 k mu sum over s bs dagger of Cs dagger of k Cs of k minus ds of k ds dagger of k. Now, you want to consider it inside the normal ordering. So, you have the normal ordering and then the normal ordering makes this to move to the left, but it crosses once, therefore, it will change the sign, and hence after you take the normal ordering you will get dq k over 2 pi cube m over k 0 k mu sum over s Cs dagger of k Cs of k plus ds dagger of k ds of k. Okay. So, you can take the energy operator for example, and then you act on particle states like this Cs dagger of p one particle states or ds dagger of p acting on vacuum or so on, and then you will see that this will have one quantum of energy and so will this state have. There is nothing negative about this thing. I mean, it is not a negative energy state. You can just act, you can this is the p mu, you consider a state like this or you can consider a state like this p 0 on Cs dagger of p 0 or p 0 acting on ds dagger of p on vacuum. You can see that both type of these particles have positive energies. So, the energy, they are eigenstates of the energy operator and the eigenvalue is always positive. So, these are not negative energy states. Only thing is that if you consider the charge operator, if you construct the charge operator and then you act on this as well as on this, then the eigenvalue of states of this kind will have opposite eigenvalue for the states of the second kind. So, it is only the charge which is negative of this charge of these states is minus of the charge of these states, but the energy eigenstates are not negative. I mean, the energy is always positive. You can write it in terms of the number operator. For example, you can introduce an S of P equal to Cs dagger P Cs P and Ns bar of P to be the number operator for the antiparticles ds dagger of P ds of P, then this will have simply Ns plus Ns bar. So, these are basically the Cs dagger, Ns are basically the annihilation, creation and number operators for particles, whereas ds dagger, Ns bar are the annihilation, creation and number operator for the antiparticles. Alright, so what we will do in the next class is we will consider some of the discrete symmetries, and also we will derive an expression for the Dirac propagator, and then subsequently we will learn about the interaction of fermions with the electromagnetic field. Okay.